Okay, so a new booklet, electrical sources and internal resistance and capacitors. So this is the last new booklet that you're going to see because the last bit of electricity is semiconductors that you have seen before, but we'll hopefully have time to go over it again. So there's quite a bit of new stuff in this booklet compared to the last one. So we're going to look at internal resistance. So that's basically a battery has sort of basically a mini resistor inside of it, so called internal resistance. So you don't get the full potential of a battery or a cell out. So there's a new equation for that, which is it's basically just another version of V equals IR. And just a few new definitions of things that maybe we've been calling something else up until now. And also capacitors. You have looked at capacitors, you know what they do, but we're going to look into quite a bit more detail about capacitors and how they work in higher as well. So a few more equations come across that are related to capacitance as well, and a little bit about how they charge and discharge. So we're going to start off with the internal resistance side of things. So voltage sources and electromotive force, or EMF for short. So cells, batteries, power supplies and generators are examples of voltage sources, so anything that provides a voltage. An ideal voltage source would produce a constant voltage at its terminals regardless of the current being drawn from the source. And this voltage is called the electromotive force, or EMF. So basically what the EMF is the ideal voltage that would come out of a battery if we got the whole amount that it could supply. Now that doesn't really happen in real life when we attach things into a circuit, but the electromotive force, EMF, is the total voltage that could come from a cell or a power supply. So a definition for electromotive force, and they do quite like asking definitions. So it's the energy given to each coulomb of charge by a source of electrical energy. And it's measured in volts, and 1 volt is 1 joule per coulomb. So energy given to each coulomb, so 1 joule per coulomb. For example, the EMF of a cell is the number of joules of energy given to each coulomb of charge by the chemical reaction within the cell. It's measured in volts, and an EMF of 1 volt means that each coulomb of charge requires 1 joule of energy. So the EMF, as I said, is the maximum the voltage available from any source and is measured when no current is drawn to an external load. So you've got nothing in the circuit. In other words, it's the voltage measured across the terminals of the cell when there's an open circuit. That means if you basically just go from one end of the cell to the other, so like maybe a spanner drops across a cell, the terminals of a cell or something like that. So there's nothing in the circuit. As soon as you put something in the circuit, the voltage supplied to the circuit drops a little bit. So real voltage sources do not behave in this way. They don't give you the total available voltage. The voltage reading that is measured by a voltmeter connected across the terminals of a supply is called the terminal potential difference. So this is the voltage that we actually get out. Okay, so the terminal potential difference is the voltage that goes out and gets applied to whatever is in the circuit. So the terminal potential difference is always less than the EMF because we lose some voltage. We lose some voltage when we stick things into a circuit. So the terminal potential difference is what actually gets applied to the circuit. The EMF, it will be the perfect voltage, but that drops as soon as you put something in the circuit. So the terminal potential difference is always less than the EMF whenever current is drawn from the source, and it gets smaller and smaller as more and more current is drawn from the source. This effect is demonstrated when a car sitting with its headlights on is started. The starter motor draws a large current, and this makes the terminal voltage of the battery drop so much that the lights dim. So if you've ever been in a car like that, when the headlights are on, the starter motor starts and the lights dip a little bit. That's because the terminal potential difference, the available voltage available to the car itself, decreases. So EMF is the total voltage that you could get out if it was perfect. The TPD is the voltage that does come out and gets applied to the circuit. The internal resistance is that sort of imaginary resistor that's inside a power supply, or we call it, we basically say that the power supply, a battery itself or a cell itself, has a little resistance inside of it as well. So it makes sense to consider that every real voltage source has an EMF with a resistor. Oops. In series with it. And voltage drops occur across the resistor inside a supply. This is known as internal resistance. And cells can be represented like this. So you can see here. So you think of the yellow cells that I have in my lab. This is the whole of the yellow cell. And inside that yellow cell, there's an EMF, so that's sort of the perfect voltage, and a little mini resistor. Okay, and that little mini resistor is lowercase r, and it's called the internal resistance. It's the resistance inside of a cell. Okay, so if you think about it, just a normal AA battery, the total battery, what comes out of it would be the TPD when you plug it in, when you stick it in any electrical supply, anything electrical. But inside that little AA battery, there's a perfect voltage, an EMF, and a little mini resistor. There isn't actually a little mini resistor, but it acts like one. So we call capital E for short is the EMF measured in volts. So that's what the total voltage you could get. And lowercase r is the internal resistance measured in ohms. Okay, so every power supply has an internal resistance. So the effect of internal resistance. So if you had no load across the terminals of a cell and no current drawn, which we call an open circuit, the terminal potential difference is equal to the EMF. So we get the whole package. That's if no current is drawn, if nothing's plugged into the circuit. So if no current is drawn, there is no voltage across the mini R, the internal resistance. But if you add anything into a circuit with a load resistor R, so in this case we're adding a resistor into the circuit, so a resistor capital R, and it's connected across the terminals of the cell, and therefore there's a current flowing. So that means that the EMF capital E will be bigger than what actually comes out of the cell itself. So with a load resistor R connected across the terminals of the cell and current I flowing in the circuit, a voltage develops across the internal resistance. This voltage is not available to the load resistor R in the circuit, and it's called loss volts. So to calculate loss volts, it's just like you would calculate any kind of voltage. It's current times by resistance. So in this case, for loss volts, it would be the current times by lowercase r, their internal resistance. So that loss volts is I, the current in the circuit, times by internal resistance. Okay, so for example, EMF might be, the total voltage might be 2.5 volts, but the TPD, the actual voltage that gets applied to the circuit, could be 2.4 volts. So the loss volts would be the difference between those, so 0.1 volts. So you have an EMF, you have a total voltage, you have a TPD, the terminal potential difference that gets applied to the circuit, and you have that loss volts, which is the difference between the two. When current is drawn from the cell, the terminal potential difference will be less than the EMF. So the terminal potential difference is the EMF take away the loss volts. Okay, so the EMF, in other words, the EMF in total is the terminal potential difference plus loss volts. Okay, so the EMF is the whole voltage, the TPD is the voltage that gets applied to the circuit, and the loss volts is what's in the volts that are lost inside the cell. So in symbols, TPD we call V, equals EMF minus lost volts, which is capital I times by little r, lost volts. If you're not given a diagram, sketch one to help you solve the question. It does help. And it does help to draw sort of the dotted line around an EMF and an internal resistance. So from the law of conservation of energy, we know that the EMF is the terminal potential difference plus the lost volts, which we just said earlier. So the EMF, capital E, is lost volts I times little r plus V, the terminal potential difference. Terminal potential difference, that V, is the V given to whatever's in the circuit. So in this case, it's just the voltage across that one resistor. So the voltage across that resistor is I times the capital R, the resistor. So lost volts plus V, which is IR, is the current times by the internal resistance plus any external resistance. Another way of looking at it, if this helps you, is if you redraw this diagram, we've got our EMF there, we've got an internal resistance, and we've got external resistance. If you wanted to, and we've got current going around, if you wanted to look at it this way, you could say that EMF is just our total voltage applied to that circuit. V equals IR, so the total voltage, so let's say E total is the total current, which is the same at all points here, times by the total resistance. And the total resistance in this circuit is R, capital R plus lowercase r. So you could look at it in that way if you prefer. It's completely up to you. Okay, you just need to remember that there is internal resistance.